Good morning, ma'am, and thanks for accepting our invitation and giving the seminar for AppCare IEEE Symposium. So, Dr. Divya is an assistant professor at the School of Mathematics and Computer Science at IIT Goa. Previously, she was a research fellow at the Singapore University of Technology and Design. She received her PhD from Department of Computer Science and Automation at IISc Bangalore and holds MTech and BTech degrees from IIT Madras and NIT Calicut respectively. Thank you, ma'am.
Yeah. Yeah. Thanks, Srini, and thanks, Nehanshu, for inviting me to give a talk at AppCare IEEE Symposium on AI and ML. The talk today is on the role of submodularity in influence maximization. Um, what I'll do is I'll introduce the influence maximization problem and then talk of some aspects of submodularity, which is a property of set functions. And then I'll talk of how submodularity plays a role in influence maximization. Influence maximization is a very classic machine learning problem. I mean, classic AI problem, I should say. And after this, after I've said the base, I'll just talk of some recent research directions as well, some recent research results that we have got, again, which exploited submodularity in the same context. Okay, so to just talk of the influence maximization problem, you can think of the situation where you want to, spread some information on a network. Maybe it's about some event, or maybe there's a new product that you have and you want to spread, I mean, you want maximum people to get this information. And so what you could do is, today there are a lot of these social networks you could make use of. And then you choose a few people and you brief them about whatever your product is, or whatever the event is. And the idea is they in turn will spread the information in their network. Okay. So these people are called the influencers. This is one way of spreading information, okay, disseminating some news. And so more formally, there is a network, okay, a social network, which is modeled as a graph with V, the set of vertices, and E as the set of edges. Okay. And so what you have is you have the connection network, the connectivity network, who is connected to whom. Okay, so that is basically this graph. And the idea is to choose a set of K nodes. So K is something like your budget. Okay, so you can maybe choose 10 influences or 15 influences. So that value is K. And the seed set is the set of people whom you choose, the set of vertices, essentially, that you pick as the influencers. And they are in turn able to, spread the information. And the idea is that you choose this set so that they can in turn influence the maximum number of possible nodes in V. Okay, so this is a problem, which is the set that you choose, which is a set of K nodes that you will pick so that the information spreads in the network. Okay. Um, yeah, so this is the problem. And the issue here is that, okay, as such, you might think maybe, pick the ones who are connected to the most number of people, okay, who have most number of friends, okay. But the issue is that they might be connected on the network, but the true nature, whether they really influence the other person, that is sort of unknown, and it's a random quantity. For example, in this network, maybe 1 and 5. Okay, so there is a connection between them, but you don't know about the strength of the connections. They are connected on the network, but does the person 5 really buy what the person 1 says? Okay, or, or do they have a negative influence sort of a relationship and so on? Okay, so in essence, the edge activations, though there is an edge connecting these two, the activations are unknown and it's a random quantity. Okay, and what we will model it as, with a as a Bernoulli probability. So probability of the Cij between edge for edge ij, probability that it is 1. So which means that this is an active edge. So, or in term, that probability that I influences j, that is a value small pij. Okay, it's a probability. And there's a famous influence maximization model. So there are several models. One of the famous ones is the independent cascade model, which was introduced in this paper in 2003. Okay, and here all these edge activations, there are various edges, and all of them, the way they are modeled is via a joint independent model. So the joint probability is an independent distribution. Okay, and so Pij is each of the Bernoulli probabilities. Okay, and just some notation. So R of Cs. So this is what we'll use to represent the number of nodes that you can reach with a seed set S under a configuration C. Okay, so C is actually a random quantity, but if you're given the exact value C's, which is a vector of either of ones and zeros, then R of CS is the number of nodes in that network defined by C that S can reach. Okay, and so because C is a random variable, you can talk of expectations, and the underlying joint distribution is an independent distribution. So the expected number of nodes reached under this distribution, so that distribution will refer to it as theta IC, and the value is expectation of RCS. So that is the objective FIC. Okay, so the expected number of nodes reachable by seed set, this is what you want to maximize, and subject to the condition that the seed set has at most k nodes, because you can only, and that's your budget. Okay, so this is the problem. This is a classic influence maximization problem under the independence cascade model that you try to solve. Okay, so now before I actually get into how you solve this problem, I'll talk of submodularity because it's a key property which is being exploited in this seminal paper. So what does it mean for a function to be submodular? Okay, so it's a set function basically. It's defined on a set, and so suppose you have a set of elements v as 1 to n, or just the collection of some elements, and A and B are like two subsets of V, such that A is in turn contained in B. Okay, so then let's talk of F as some sort of a utility or a benefit or that kind of a function. And now you have the set A, you're trying to put in a new element X into it and see how much X contributes. Okay, so this F of A union X minus F of A, that is like the marginal benefit that X contributes when it's included in A. And on the right hand side, you have the marginal benefit when X is included in B. And B is a larger set. So what submodularity says is that if you include X into a smaller set, the marginal benefit you get is more, okay, than when you include X into a larger set. So I've just depicted this with this example. So there's popcorn and you're trying to include a drink along with a set which has only popcorn. And now the set B has popcorn and something else, some other element, maybe another drink. Now the benefit of including this red drink is more when it's included onto the set A, because there's just one item. But if you have more items, the satisfaction you get of including a new element is less. Okay, so that's what submodularity says. And there's also an alternate definition of submodularity. So this first inequality is what I talked of. So this is actually the property of diminishing returns. And there's another characterization like this. So here, the second one, A and B, they don't need to have a subset relationship with each other. So any two subsets you take of V, you will have that f of A plus f of B is greater than the sum when you take unions and intersections. Okay, so personally, I find the first one to be more intuitive, but actually both these are equivalent ones. So to test the submodularity of a function, you could use either of these properties. Okay? And the thing about submodularity is it shows up in several applications like sensor placement, active learning. Active learning is a proper paradigm of machine learning. And of course, influence maximization, as you will see, and some things in game theory, information theory, and so on and so forth. There's a whole lot of literature out there. And so there's a useful reference below. It's a tutorial on submodularity, which I would urge you all to take a look at. Okay. So I'll just talk of some examples of submodularity before I get into influence maximization and how it exploits submodularity. So the first example I have is on the maximum of a set of elements. So suppose V is now set U1 to UN, and I'm looking at the max element of this. Of course, u1 to un are all numbers, and I'm looking at the max element in S. That's my function f. So this is actually a submodular function. And if you want to show this, you can just try to verify the property that I showed you, the diminishing returns property. You take two subsets of V, S and T, such that T contains S, and you take some element V which does not occur in S or T, so which is outside both these sets. And now what you want to see is, if you bring in V to S, what is this difference? Okay, so remember we are looking at the max function. So this difference, it will be zero if, if there is some other element in S which exceeds V. Okay, and so in that case, both these f of S union V and f of S will be the same, so it will take a value 0. And on the other hand, if V dominates every other element in S, then this difference is going to have a non-zero value, and in particular it's a positive value, and that's going to be V minus the max element of S. Okay, so that is one term that you want to look at. And the second term is the same thing, just that instead of S you replace it with T. Okay, so it has that kind of a structure. It's either it's either 0 or this difference between V and the max element of the set you're looking at. Okay, so now one thing is, if you remember that S and T, they have a subset relationship. So S is contained in T. So if you look at max U and max U in S and max U in T, so you can sort of write this on this number line where max U over S, and that's going to be less than max U over T because T is a larger set. Okay, and now in terms of the value of V, there are three possibilities on where V will lie. So case one is when V lies to the left of max over S. Okay, so this is the one red that I've shown. So in this case, V is going to be less than max over S and also less than max over T. So both these terms, T1 and T2 that I've written here, evaluate to 0. Okay, so then this is fine. Now, in terms of case 2 is where V lies between the max element of S and the max element of T. So here, if you look at T1, you're going to get a value which is greater than 0 because V exceeds max element of S. But T2 is going to be 0 because V lies below the max element of T. Okay, so here we're going to get T1 is greater than 0, actually strictly greater than 0, and T2 is equal to 0. Okay, so we have shown that T1 is greater than T2 here. Okay, and the final case is when V lies to the right of the max element of T. So V exceeds the max element of T. So here, if you see, both these terms T1 and T2 are going to be greater than 0. And in particular, V is going to be, closer to the max element of T because it lies beyond the max element of T. And so the difference, V minus max element of T, is going to be smaller than the difference between V and max element of S. Okay, so T1 is going to be greater than or equal to T2, and so even this case is taken care of. So these are the only three cases, and in all these three, we have the diminishing returns property. So that's why the max of a set of elements, that is submodular. Okay. Now, the second example I have is on the coverage function, what's known as a coverage function. So it's actually something which shows up in applications like sensor placement. And, if there are people who are attending this event from Bangalore, about the water shortage that's going on in Bangalore. So there are these various taps that have been installed in various locations. So you can think of, what are these locations where the taps should get put. Okay, so I'll just illustrate this with a figure, and then I'll talk of, how you show this is submodular. So there are a couple of elements U. So let's think of that as locations. Okay, so there are a couple of locations on a map, and there are some subsets. So S1 to Sn. So you can think of these as locations corresponding to a tap. For example, if I place a tap at this location and this figure at S1, then there is a whole region that gets covered by this one tap. Okay. Similarly, if I place a tap somewhere at S2, there is this whole location, set of locations, it gets covered. Okay, so that is this S1 to Sn, the set of locations that is covered by tap 1, tap 2, and so on up to tap n. Okay, and so the idea is you want to find, where to position these taps, or in sensor placement, where to position sensors so that, maximum regions are covered. Okay, and so this F is defined as a number of elements of U, the overall set of locations that is going to get covered by this collection of subsets. So S is itself a collection of subsets of N. Okay, so if I say S is 1, 2, 3, so then what it means is I'm looking at S1, S2, and S3, and I'm looking at all elements of S1, S2, S3, or the number of elements in S1, S2, S3. Okay, so that is what is F. Okay, and so this is a submodular function. So here, I mean, the math is, it's not too hard, but pictorially, if you see, if I'm trying to bring in S dash, so I've already put my sensors or taps in S1 and S2. Now, if I'm trying to bring one more tap at S dash, okay, and this S dash caters to this region in red. Okay, and so the additional space it covers over S1 and S2 is this sort of region. Okay, but without the overlap from S2. So whatever that doesn't overlap with S1 and S2, that is the benefit I get. Now, versus if I had S1, S2, S3, S4, I already had 4 taps. And now I'm trying to bring in S dash. The region it covers is the bright red part, the bright red shaded region, which is going to be much smaller than when I would have included S dash into S1 and S2. Okay, so this is again what is submodularity. Okay, and in terms of the math, it's just the consequence of, the reach being more for larger subsets, and so the overlap with S dash could just be less for larger set. Okay, so so this is actually a very useful example, and there are examples like this even in active learning. So yeah, this is a very famous example. Now, the third example I have is a graph theoretic one, which is of cut capacity. So there's a graph with vertices V, edges E. It's a weighted graph, and Cij is the weight of the edge ij. And let's say all these Cijs are non-negative numbers, in fact, even non-zero. And let us say f of s is the capacity of the cut induced by s. So what that means is that you take all the edges which go out from s onto v minus s. You take each of these edges, look at the capacities or the weights of that edge, and the sum of these, that is said to be the capacity of that cut. Okay, so each subset of vertices induces a cut in the graph. Okay, and that sum of those capacities is the capacity of the cut. So now it turns out that this is a submodular function. So in order to see this, we can just look at again the diminishing returns property. So there's a set S onto which you're trying to bring in a vertex V. Okay, and so this difference, the marginal improvement that you get, it's just going to be the difference between the cut induced by S union V and S. So the sum, I mean, whatever is there in S, the edges contributed by, one side being in S, that those actually cancel out between both these terms. So what just remains is the edges which go out from V. Okay, and so this sum CVJ is what matters. Okay, and so there's some edges which, I mean, they don't belong to T. Okay, so there are some vertices here in the red color. Those vertices don't belong to T, but they're connected to V. So those capacities come in. And when you look at this f of s union V minus f of s, additionally, you also have some vertices within T but not in S, which are connected to V. So even those come in, those play a role. So the green edges basically. So sum of the capacities of the green edges and the red edges, that is what is one of the terms. Okay, the first term. And whereas if you look at f of t union v minus f of t, only the red edges would remain because you're trying to see everything which goes out of t. Okay. So because all these capacities are greater than zero, all these weights are greater than zero, the first term is larger than the second term. And so there's more benefit of including V onto S than onto T, onto a smaller set than a larger set. Okay, that's about the cut capacity. Um, One thing here is the previous two examples that I showed you, the coverage function and the max of a set of elements, these were monotone functions. By that, what I mean is that f of s for a smaller set would be smaller than f of t for t, which is a larger set. Okay, so this was obvious here, and we made use of that property here. So it's monotone. Similarly, it's true for the coverage function. If you have more sensors or more taps, you can cover more area. Okay, so that's for the coverage. But cut capacity depends on these C's. It's not necessarily monotone in this case. That's just something, a fact to remember. Now, the final example I have is the influence function, because we're going to talk of influence maximization. So here, think of the deterministic graph where there is no issue of, who influences whom, that the fact that you don't know whether somebody influences another. You just have V and E, the set of edges. And so f of s is the number of nodes reachable from S, the subset S, via some path. Okay, so there's some vertices, which are the vertices in capital V that you can reach through some path. Okay, so that is f of s. So here it should be obvious to see that, if you include some vertex V onto a smaller set, there is more benefit than including onto a larger set. Okay, because this difference is just the number of nodes reachable from V but not S. Okay, and reachable from V but not T. Okay, so T is a larger set. So there is a chance that some things that you could reach from V, you could reach from something in T itself. Okay, it was a larger set. And maybe that was not the case with S. Okay, so because of this, you have, submodularity is quite obvious here. Okay. So this is about the influence function. So the influence function in the deterministic case, it is submodular. Okay, so here we didn't say anything about probabilities. The graph was given, and that is the friend network. And the assumption is that if there is a connection, the edge is active. Okay, so or that if ij is an edge, then I influences j. Okay, so if that is the assumption, then the function is submodular. Okay, so now why am I talking so much about submodularity? What is the benefit of it? Okay, so some properties of submodular functions which are good to know. So one is minimizing a submodular function. This is actually, it turns out it's polynomial time solvable. Okay, so we're not going to delve too much on it here. So there's something called the Lowa's extension. So remember, submodularity here, we are talking of set functions, or these are discrete optimization problems. The idea in Lowa's extension is to extend it to a continuous space and then use techniques from convex optimization there. Okay, so it turns out that it's a very special way of extending this f of s to a continuous domain. And it turns out that when you do that, you get a convex problem. And so that's the reason why min f of s is polynomial time solvable. On the other hand, the problem that's important for the purpose of this talk is the maximization of the submodular function, subject to this sort of a cardinality constraint. So it turns out this is a hard problem. It's an NP hard problem. Okay. So what is the big deal? So why are we even talking so much about submodularity? The good thing is, even though this is an NP hard problem, maximizing a function, a submodular function subject to a cardinality constraint, the thing is that there's a greedy algorithm which you can write. So you want a set of k elements. So the idea is that you start off with a null set, and each time you try to find out an element from your base set which contributes the most to your function, and then you keep including that into your set. Okay, so that's a very simple greedy strategy. And it turns out that such a simple strategy has really good approximation guarantees when the function that you're looking at is monotone and submodular. So monotone, by that I mean that larger sets have larger f values. And submodular, we saw what it is, the diminishing returns. So if your f is monotone and submodular, the greedy algorithm in this sort of computation gives a set S. Your final set Sk that you get will have a value of f which is at least 63% of the optimum. So S star is the best that you could do. You couldn't get f of S star, but what you could get was this 1 minus 1 by e factor approximation guarantee for this greedy algorithm. Okay, so that is a nice thing. So not all is lost. And another important thing here is you can't do better than this for these kind of functions in general. I mean, of course, maybe for very specific objectives, maybe you can do something better, but as a general class, this is the best you can do. Okay, and so this comes from an earlier from a seminal result of Nemoser. Okay, and one important thing here is that this result assumes that you can compute f efficiently. So there is, at every step of this iteration of this greedy algorithm, there is a function evaluation which is coming in here. And so if you can do this computation of f efficiently, this is the result. Okay. So now coming back to influence maximization problem, what we saw is the influence function is submodular if it was deterministic. So now there are also some other properties which we'll exploit of this influence maximization problem. So here there's a seed set which you're trying to, ensure that it reaches to maximum number of people. So there's a set S and you're trying to measure how many other nodes it can reach. So it turns out that to compute the influence function, you can actually write it in terms of a max flow problem, a network flow problem. So the way to do that is introduce two auxiliary nodes, S and T. So this is like a source and destination nodes in the max flow terminology. So connect S to small s, the new node small s, to everything in your seed set, S, and connect everything which is outside S to the destination node T. Okay, and then if you set the capacities of all these nodes, of all these edges as some value v minus s times Cij. So Cij is 1 if node I influences node G. Okay, so let's take for now, let's take that it's deterministic. Okay, so then this sort of capacities and make of course all these xjt's. So for everything, all these red nodes which are connected to T, those have capacity of 1. So if you try to find the value of the max flow problem on this sort of a new auxiliary graph, then what you get is the total number of nodes outside S that you can reach. Okay, so that is Z of CS. And so the total number of nodes effectively reachable is, of course, you can include S itself. You can reach yourself. Okay, S plus Z of CS, where Z of CS Z of C and S, that is computable using a max flow problem. Okay, so this is a case when C is deterministic. Now, this kind of an interpretation as a max flow problem, there are some consequences of it. And one thing is that, of course, we saw that our CS is submodular in S. Okay, and now if you look at the random graph context, okay, but whatever happens in influence maximization, there are these edges, but you don't know how active they are, whether they're really influential or not. It's just the connectivity graph. So in that case, the graph structure is random. Okay, and so the expected value, which is a non-negative combination of various RCS, that is also submodular in S. Okay, so that is a property of submodular functions. If you add two submodular functions, you'll get submodular. Weighted sum of submodular functions with the weights being non-negative, that's also going to be submodular. So an expected value of a submodular function, that's also submodular. Okay, so So what happens is, one good thing is, because the expected value is submodular, and remember in the independent cascade model, the distribution, underlying distribution was given with independence. So you can apply whatever results we have, maximizing the submodular function using the greedy algorithm, and you will get the desirable results. 63% approximation guarantees you will get. Okay. So only catch is that evaluating this expectation is expensive. Okay. So remember when this greedy algorithm, when I showed you, there was the step of evaluating the function at each iteration. So if that is doable efficiently, this is fine. Okay, you'll be able to easily do this computation. But here, what happens is, evaluating this expectation is expensive. So you have to go for some other ways, some kind of approximations. Okay. So now what I'll do is, I'll get into a more recent model, some research which allows us to tackle this, this issue of evaluating this expectation, that being expensive. So we will look at a slightly different model, a more robust model. So the question we are asking here is about this independence assumption. So in the influence maximization problem, what I told you is, in the independent cascade model, all the edge activations were considered to be independent from each other. So that was a joint distribution. Okay. But how are we always sure that there's no relationship in the way people influence each other? Right. For example, if I'm trying to influence couple of people, there might be some relation in the way I influence one person and another. Okay. So just assuming independence is maybe not the right thing to do. Okay. So what we instead assume is, we only know those PIJs. The probability that I influences J is PIJ. Okay. So we only know those marginal distributions, but we don't know how the coupling is happening. Okay. So there are now a set of possible joint distributions. Okay. But all of them, the common thing about all these joint distributions is that if you look at the particular ijth component, okay, those are all going to have the probability Pij. Okay, but you just don't know if they are going to be the way they are joined together. It could be independence, it could be very perfectly positive relations between them, or it could have negative relations. All of these kind of relations are allowed. Okay, so there's a set of possible joint distributions here. And now, once there's a set, okay, of possible distributions, if you take a seed set S, there are any of these distributions could manifest. Okay, so what is the worst possible expected reachability you can get from a seed set S? Okay, so that is F core, what we'd refer to as F core. And one value is, one possible element of this capital theta is the independent set. Okay, so F core of S would be lower than what you would get with independent cascade. But then what you're trying to do is, you're trying to get a robust seed set, or a distributionally robust seed set, such that this F core of S is maximized. So there's a worst reachability from a seed set. And can you find a seed set now which maximizes the worst case reachability? So it's a sort of adversarial strategy that we are trying to focus on. And there's a two-stage problem here. The inner minimization problem, that I will refer to as the second stage, and the maximization problem, that I'll call as the first stage. And in contrast, the independent cascade just had one stage problem, but there was an expectation computation there. Okay, whereas here there's a min expectation that you'll have to compute. Okay, so now, this comes under the realm of an area called distributionally robust optimization, DRO, which is now being used a lot in ML. And I mean, it originally came up in different areas like finance and all that, but now it's being used in ML. So I'll just spend a little time on what are the possible uncertainty sets. So this was one, the set of all feasible joint distributions consistent with some marginals. Okay, so that is called MDM, so marginal distribution model. So there the univariate marginals are there, and you're trying to look at all joint dependencies. Now, you could also instead have moments of your uncertain quantity. And so then maybe you have the mean and covariance of the random quantity. So there are a couple of distributions which have the same mean and covariance. That's another example. And then we also have sample-based uncertainty sets. So maybe you don't have access to any of these statistics like moments or any of these univariate distributions, but maybe you have some samples of C. Okay. And with that, you could construct an empirical distribution and then look at all distributions within some distance from this empirical distribution. So that is your class of distributions. Okay. So these are some examples. There's a whole literature on DRO, so you can take a look at it. So the first one is this textbook on marginals on the first two ambiguity sets. And there are also some of these papers, and the last one is particularly on the Wasserstein distance-based ambiguity set. Okay, so there are a couple of things here. We'll focus on MDM for this work. And yeah, so I'm not going to delve too much on this result, but this is something which is useful, especially in this context of influence maximization. So suppose there is a combinatorial problem like this. Okay, so there's a max C transpose X, and where your X lies in some polytope, and this polytope has all 0, 1 valued points. Okay, so this is like what happens in the max flow problem. Okay, so in this case, if your C, your objective function, this linear objective. So in this case, yeah, so if your objective is linear, then what happens is if you're trying to find the max expected value for MDM, okay, for the marginal distribution model, there is an equivalent reformulation. Okay, so this right side, what I've shown you is the equivalent reformulation. So it's in terms of a deterministic computation. So C is a random quantity. And here what we have on the right hand side is instead of evaluating the max expected value here, you can evaluate the value for a deterministic problem D, Z of D. And so it's as if you're approximating this with Z of D. But then there is a penalty because you're choosing D instead of expectation of over C. Okay, so then that penalty is quantified by this expectation of C minus D plus. Okay, so this, of course, it's not very obvious, and I mean, there is a detailed proof which is there in a very seminal work, okay, which I've given a reference here. So the idea here is that if the deterministic problem, Z of D is a deterministic problem, of course, you're trying to now find the coefficients D here. If this is easy to compute, then your max expectation is also easy to compute. Okay, and this is the result of Melitson and others, and you can analogously derive the result for min value, min expected value of a form like this, min C transpose X. Okay, so this is what we will use, what we have used in the influence maximization context. So if you try to plug in this formulation, so remember we were trying to find the second stage problem. There is a seed set S. You're trying to see how bad the expected reachability can be, okay, in this class. So now if you try to apply this formulation, what you get is, I mean, of course, there's a lot of simplification and all that. But then finally, what you get is a simple looking linear program which computes this min expected value. Okay, and in particular these constraints actually turn out to be, I mean, this LP itself, it turns out to be a reformulation of a min cut problem, the max flow min cut, right? So min cut is the dual of the max flow problem. Okay, so this turns out to be exactly corresponding to a min cut problem with capacities defined like this 1 minus Pij. Okay, and so that's one good thing, that this min expectation is sufficiently computable. And these variables, pi i's, they have an interpretation of the probability of reaching the node I from S, okay, in the worst case. So remember, Pij is the probability that I influences J. And pi I, you can think of it as, in the worst case, what's the probability that node I, which is in V minus S, can be reached. Okay, and so you see that pi I is 1 for everything in S. Every node in S is, of course, reachable by some node in S, right? So that's why pi I is 1. Okay, so the advantage here is that the worst expected reachability that can be computed now in polynomial time because this is just the linear program. But the expected reachability under the influence, under the independent model, that couldn't be computed in polynomial time. Okay, so that's an advantage here we get. And yeah, there's also shortest path implementation, I mean, shortest path interpretation for this LP. It's min cut, and in particular, it's a shortest path sort of a thing. I mean, it's not very critical, so in the interest of time, I'll skip this. Okay. Now, moving on to the first stage decisions. What we said is if there is a seed set S, you know how to compute the worst case reachability. Okay. But now how do you maximize, how do you find the seed set which maximizes this? So there's a two-stage problem. You can use, again, the dual of this problem which I've given in red. And so you'll get a max problem and jointly do some optimization. So the issue is that you'll get some quadratic terms which you don't know how to deal with. They're not convex also. Okay, so there are some approximations you can do. So I'll not spend too much time on this. Again, I think I'm running out of time. Okay. Um, so the idea is that you can write a mixed integer linear program to compute the first stage decisions, but it may not be, I mean, it may not be computationally feasible. Okay. So here is where, again, submodularity helps. Okay, so if you remember the independent cascade that we talked of, that exploited submodularity of the reachability. And one good thing that happened is the expectation of R of CS, that is submodular. But the issue is that in general, min of submodular functions, that is not necessarily submodular. Okay, so that is, we don't have a general result there. But one good thing that happens in this case, it's very specific to influence maximization, is because the worst expected reachability is monotone submodular. I mean, that is because it's a min cut formulation, it is also monotone submodular. So because it's a cut capacity sort of a framework. Okay, so again, you can just apply Nemos's greedy algorithm and get the 1 minus 1 by E approximation guarantee. Okay, so that's where submodularity really helps, even in robustification. Okay, so just a comparison of these two models. Independent cascade, you were looking at the expected reachability under independence, whereas in robust, you were looking at the worst case. Okay, so the function was NP hard to compute. This expectation itself was NP hard to compute in independent cascade, but our robust model, it was easy. And both these are NP hard problems. If you want to maximize the expectations, both are hard. Okay. And both have submodularity. So because of which you can apply the greedy algorithm. And the approximation guarantee for the robust model is 1 minus 1 by E. There's a minus epsilon factor here, and that comes up because this function is not easy to compute. So you have to do some sort of sampling, and because of that, there is an error. Okay, that's this epsilon. Okay, so there's some experimental results that I have, but how am I doing on time? Is there time to delve a little bit on this, or?
You can proceed like 5-10 minutes is fine.
Okay, fine. So I'll be done in about, I think 5 minutes should be good enough. Okay, so since we talked of two models, the independent cascade and the robust model, just some findings from some experiments. So we had these two data sets, the Wikivote and poll blogs. Okay, so these are actually data sets which are available freely. Okay, so poll blogs is about political blogs and stuff, and Wikivote is about voting. Okay, so here the vertices and edges, this is what the configuration is. So these are sort of large networks, and there's some statistics of the degrees of the nodes. Okay, so the number of connections per node and stuff. Okay, and so what we do is we have a greedy solution to the robust model. Okay, the greedy algorithm for the robust model that we call as S-core G, and greedy solution to the independent cascade, that is SICG. So this is not, yeah, of course, there is some, because the expected value under independence is not exactly computable, we have to do some sort of Monte Carlo simulations. Okay, and so we used some variant, I mean, to speeden up the computations. There's something called the accelerated greedy, which you can check out. Okay, this was used to speeden up the greedy algorithm for independent cascade. Okay, and we have this code which is available. You can check it out. Okay, so what we did is the first thing is, if you set the PIJs, there are various ways in which you can set PIJs, the probability that I reaches J. So this is simulated from uniform distribution 0, 1. Or there was another configuration where we picked one of these three values, 0 0.1, 0.01, and 0.0001 with equal probability. Okay, so this is like very small probabilities. That's what we wanted to see how it performs. Okay, so there are these three sets that we get depending on whatever PIJs, I mean, so these two sets and then these two data sets that you get under different values of PIJ. So here what we have is, we have one thing is the nature of the seed sets. So the degrees, right? The min degree, the average degree, and the max degree. So if you take the seed sets that were produced, how many nodes was it connected to? Okay, so one thing that we found in score G is that it always picked, on an average, it was picking, high degree nodes. Okay, so 288 versus 192 for this case, 159 versus 116, and so on. Okay, and so in terms of misspecification ratio, so what we mean by this is score is what was meant for the robust model. Okay, now if you evaluate it under the independent cascade, how does it perform with respect to what was truly meant for the independent cascade? Okay, so similarly for SICG, if the worst case was what happened, that would have been F core. How did it perform compared to S core G? Okay, so the misspecification ratios here, if it is higher, it's better. Okay, so it means it's more adaptable for the case where I mean it's a measure of robustness basically. So here we see that S core G is typically having a higher misspecification ratio. Okay. And so again, some more details about the degrees of the nodes. If you look at the histogram of the nodes which are produced by these two seed sets, clearly you have S core G having picking higher degree nodes. Okay, so this is for the pole blocks data set where K is 40. So our seed set is, we are constraining it to have a size 40. And so here you see that score G has couple of nodes in this range from 150 to 400. And whereas SIG is just restricting it to 140. Okay, beyond 140, there are no nodes. So in some sense, the robust model is preferring high degree nodes. Okay, and again, on the model misspecification, some more insights here. So here we were varying the marginal probabilities P from 0 to 1 and just looking at what happened to the expected influence under various contexts. So if you look at S core G, okay, so the blue curve, okay, so F core of S core G, so that is what you expected to get from S core. But then if actually independence was what happened, you'd have got the orange curve, FIC of S core G, how S core would have performed under an independent cascade setup. So that's the orange. And you can see that it's not too far from the red curve, which is how the seed set which you got from the independent cascade performed under independent cascade. Okay. So in that sense, you thought you would get the blue curve, but you got the orange curve, which is not bad. Okay. But on the other hand, if you look at SICG, so the independent cascade seed set, so you expected the red curve, but then what you would have got if a worst case model happened was the green, okay, which is quite different and it's quite suboptimal. Okay, so in that sense, robust models would be what you'd prefer. So you can see similar things with the pole blocks dataset also. So to conclude, what I want to say is that we had an initial model which was based on submodularity for influence maximization. It was useful in that context to solve the problem. Now, submodularity is useful even in the context of robustification, and that's what we have exploited in a recent research. So you can find our results in this NeurIPS paper, and more recently, we also have a journal version in management science. Okay, so all these robustness results are there. Okay, and there are a couple of open questions here. What about other ambiguity sets? What do you do in that case? How do you learn these PIGs? Okay, and with learning and robustness, is there something that you could jointly do? And also the notion of submodularity. When is it useful in the context of these robust models? So there's some ongoing work that we have in this domain as well. Okay, so what I would like to just, if you didn't understand many things, the take home is submodularity is a useful tool in many of these contexts. And certainly it's something that, you should take a look at, yeah, in your particular problems. Okay? So yeah, with this, I'd like to conclude and open the floor for any questions. Yeah.
Yeah. Questions? Yes, Shravan, I think. Okay. I think Srinivas, can you unmute?
Yeah, I have done it, sir.
Am I audible?
Yes, sir.
Yeah, okay, great. So thanks for the nice talk. I have a couple of questions.
Yes.
So one is, so the solutions, so let's take the simpler model where you had your Bernoulli independent joint distribution, right? So there, suppose say if I have, I mean, so these social networks typically, I mean, the graph keeps changing, right? So suppose I have a solution for one graph. If the graph is slightly modified, is it possible to use the solution that I have to get something close to optimal for the new graph?
Yeah. So what happens in this independent cascade models is there is one base graph, which is the connectivity graph. Okay. And whatever these CIJs, so actually what manifests is these CIJs, which is random. Okay. So one thing that we're doing here is we are not taking a decision once you know the influence relationships perfectly. So at the point when you're deciding the seed set, you don't know for sure how the influence relationship is going to be, and you will never know it. Okay, so that's the thing. The base graph is a constant. Okay. So keeping that in mind is what the independent cascade model does. Now, if the base graph itself changes, right? So then, yeah, this kind of a thing is not going to be directly applicable. Um, and it's also not clear whether, if you try to look at the solution for the independent cascade under both these, whether there's going to be any relationship between these two seed sets, that's also not clear.
Okay, I mean maybe if we restrict the the kind of changes that the graph undergoes, maybe I mean some kind of iterative solution could be obtained.
Something could be obtained. So robustness is actually trying to do something in that spirit. Of course, the base graph is fixed, but you're allowing the CIJs to change with different dependencies. Okay. So in terms of so if you remember the results that I showed you on misspecification, so something like this, right? So what you thought is you would have a graph of some form, but then you got something else. The relationships, the nature of relationships changed. So in that case, I mean, even there you see a lot of variance.
Yes.
So in that sense, it's not very immediate. Maybe you have to consider some very specific type of perturbations.
Correct. Yes.
Yeah.
Okay. So my second question is, so in the second model, you are kind of allowing for any kind of correlations. So can
Yes.
we restrict that class by estimating from the specific kind of domain that you are working on? Maybe that
Yes, so
could improve.
actually, yeah. So that is also something which we are kind of thinking about. So right now there is no estimation that's going on in this model. Okay, we are just saying that somehow you have the PIJs, right? And then we are just going ahead with a large set actually. So maybe there is some correlation kind of a thing. If we are able to estimate that, maybe those are additional constraints which can get incorporated here into this class.
Yes.
Yes, that will probably make it a bit less conservative in terms of the verse. So this class, as it becomes bigger and bigger, I mean, it's becoming like a very, conservative adversary.
Yes, correct. Yeah, the minimax.
Yes.
Okay. Yeah. Okay. Thank you.
Thank you. Thank you, Divya. Thank you so much. I hope to see you once you are back.
Sure. Yeah. My pleasure. Yeah.
All right.
Thanks for having
Yes.
me.
Thank you.